So what I wanted to cover today is really how we're taking forward emissions analytics mission in emissions testing. And as most of you know, we don't specialize in certification testing. We're trying to get beyond certification, what's really happening out there, and really led by real world data to try and tackle the latest and most important emissions challenges to help in our industry partners and public policy and the like. And this is very much in the mold of that, because we have been through a phase where the currently regulated pollutants have come down significantly, but that doesn't necessarily mean that vehicles are all completely clean, and that's what we want to get at today. So very briefly about us, most of you will know us, so I won't dwell on this too much, but it is our 10th birthday this year. As we were founded in 2011, we're headquartered in the UK, but we operate around the world, and we do real world testing. So we're on the road in authentic conditions all the time. As I said, we are not focusing on dyno and certification work. Cumulatively, we've now tested well over 2,500 vehicles of different shapes and sizes. Much of that goes into commercially available database, which is available and used by lots of people. And we work with people up and down the value chain, from OEMs through to fleets, consumer media and the like. We also are increasingly leading standardization of new methods. And that's in a sense doing the stuff that's outside of the direct certification regulations, and it's looking at what new methods need to be developed and what other things are not being covered by the regulations. So we see that as very much complementary. The Euro 7 context, as I see it, and this is sort of slightly standing aside from, I'm not involved in the main work of developing the regulations. It's clearly a very live discussion at the moment, and legislation is looming. The mission of it seems to be threefold. Firstly, tidying up the rather complex and in some ways deficient Euro 6 regulations. By the history of it, it's very complicated and has embedded certain unattractive elements to it which need ironing out. But beyond that, there's very much a push to expand the boundaries to make sure normal driving across the EU is covered as much as possible within certification, but also to push for a wider range of pollutants as well, including ammonia, methane, formaldehyde, NO2, VOCs, and potentially a wider list or a narrower list. That's clearly what's under discussion at the moment. Beyond that regulatory focus, I think what the various COVID lockdowns in Europe and around the world has shown that air pollution is much more complex than sometimes thought, and particularly in Europe, it's clearly not just a NOx problem. So long after the Dieselgate NOx issue is solved, that doesn't mean suddenly we have clean air. And perhaps it is really about ultrafine particles and VOCs, which are now the more important driver or constraint on the improvement in air quality. And thinking about VOCs, not just in the aggregate, but at the species level, Europe is the second biggest emitter, for example, of the polycyclic aromatic hydrocarbons, which are many of them carcinogenic. Europe is the second biggest polluter in the world after China. So to the question of, there may be other pollutants coming out of tailpipe, but they're very small and not very important. Well, actually, if you take PAHs, that's not necessarily the case. So our approach to this, we're trying to get to the bottom of, what are, beyond what may be on the table and the currency view, what are the real problems in real world conditions? Where should focus and limited resources and limited effort go to? Not everything can be regulated. And where necessary, to develop novel techniques to enable their measurement, making sure we're not governed too much by what is easy to measure. We need to, where something is difficult to measure, that's a case to develop methods of measurement, and crucially in real world conditions as well, and to avoid a simple reversion to doing it all in the lab, because that's what's possible. we clearly, it's pretty obvious to say that exhaust is a complex and diverse mixture of chemicals. So, I mean, with traditional PEMs, it's a narrow repertoire of compounds, relatively easy to measure through long-standing techniques, but actually it's much more complex soup of chemicals that are difficult to separate, often difficult to identify and quantify as well. So all those three elements, separation, identification and quantification, are vital. And particularly we're interested in getting to some potentially low concentration compounds, but that may have, even at those concentrations, significant negative effects. So to achieve that goal, so what we've done is, so we've taken, our starting point is the standard PEMS units that we've run, and they're from Sensors Inc. that we use. Very familiar probably to most of you on the call. So 1 Hertz data with the ambient condition information, OBD, particle number down to 23 nanometers. We have augmented ours by integrating an ammonia sensor as well. I'm not going to talk about that today, but that's already been deployed in our setup. But to that, then what we've done, in order to particularly look at things like nitrous oxide and VOCs, we've now coupled this with sample collection onto a variety of tubes, mainly thermal desorption tubes. So we've developed a system which integrates with the sensor's PEMS that takes a sample using a bespoke developed proportional dilution system, taking a proportion of the exhaust onto a range of tubes, but also married that with a concept of geofencing. So that enables automatic switching between tubes depending on the location of the vehicle. So in simple terms and in practice, that means we can, even though the tubes are obviously an integrated measurement, it allows us to switch between tubes, between urban, rural, motorway conditions, for example. So so the combination of the dilution system, the geofencing, and a bank of tubes, as you can see, we're able to actually break down these integrated measurements actually into the subdivisions that we are familiar to see with the standard PEMs. Then obviously it's not measuring in real time, so at the end of the test the tubes then need to be taken for analysis. So with the tubes looking at the VOCs, we use two-dimensional gas chromatography and mass spectrometry system as shown. So we go for the two-dimensional, particularly because of its separation capability. That uses an insight flow modulator from Sepsolve Analytical, coupled with a bench TOF, time of flight mass spectrometer, and a thermal desorption front end from Marks International. So this is, well proven technology, but not deployed in this situation very often. Then that covers most VOCs. The tricky one is formaldehyde because of its volatility. So we also incorporate in this DNPH cartridges, which immediately derivatize the formaldehyde into something more stable, which can then be put through HPLC, a liquid chromatography system. So putting that all together, and then for each tube, we can create two-dimensional chromatograms. So this sits alongside all the usual stuff that comes out of the post-processing files of the PEMs, then into these maps, if you like, of all the different chemicals. And here we have this is just one example, 2 dimensions of separation, and the color and the size of each of the spots is essentially the peak of individual chemicals. So the more vivid the color and the bigger the peak, the more prevalent that chemical is. And the chromatogram can be chopped up into different zones which reflect generic compounds, so the alkane area, cycloalkanes, terpenes, and particularly the aromatic, which are often carcinogens, and the nitrogen containing compounds as well. So for each of those tubes from our setup, we're able to do this analysis and look at the speciated level, what is on those tubes. And another way of looking at it, and slightly more user-friendly, is if you project it into 3-dimensional space. And here you can see, and this is one example from some of the data I'm just about to show, in terms of how you can separate compounds, which if you collapsed it into 2 dimensions, you would have lots of co-eluting peaks, lots of overlapping peaks, so you would not be able to do the separation. So the 2 dimensions is giving you the separation, but also what's striking is how the large number of compounds that exist across the whole area of the chromatogram as well. So that goes to show what a rich source of chemicals the tailpipe on vehicles is. So that's technologically how we're doing it. And as a methodology, actually, that's the bit that hasn't changed. So we've used our EQUA test cycle, which we've used consistently since 2011. It shares some commonalities, in fact, many commonalities with RDE, certification RDE, but we actually have a few variations on it that we've always designed our route geographically for consistency, but with multiple repetitions of urban and other parts built into it. So we do have an internal concept of repeatability. It's not completely heterogeneous. There are some ways in which we do use dynamic boundary conditions, but we also have part of the test, which is a more free-form test where the driver is encouraged to drive in aggressive and strange gear change regimes to test the vehicle out. So all in all, much of it exists inside the RDE boundaries, but also a portion of it exists outside the current RDE boundaries, particularly in the acceleration dimension. Also, the total length is about twice the length of an RDE test as well, so we can gather maximum amount of data. And that's what I would like to show today. So firstly, just in a way, almost for reference, I want to show you what the regulated pollutants say. So what we've done, we've taken 8 gasoline vehicles with a different mix of hybridization from nothing to plug-in hybrid. For clarity, because I'm not interested in talking about electric range today, the plug-in hybrid is run in engine-only mode. All the vehicles are either 2020, 2021 model year, so bang up to date, and tested over the last few months. And what we're really in our minds is that these gasoline vehicles can produce nitrous oxide and formaldehyde from the 3-way catalysts, but also VOCs, including aldehydes, ketones, alcohols, and PAHs may also be generated from the vehicle. But first, before we get to those, the traditional regulated pollutants for the 8 vehicles is as shown on this slide. So you'll see it's 8 different vehicles from a range from 8 different manufacturers and different powertrains, from straight internal combustion engines, some mild hybrids, 1 full hybrid, and 1 plug-in hybrid. And what you can see is on the pollutant emissions, extremely well controlled across the board. The average exceedance factor, which is my term for conformity factor, purely because I want to avoid the legal connotations of conformity factor, but mathematically the same thing. They're all, roughly speaking, 90% below the limit. So, fantastic achievement. The CO2 side is the only blot on that, in that, and obviously there's not a regulated limit for CO2, but just to ratio that to the current 95 grams per kilometer, we're on average 50% above in these real world driving conditions. So, I mean, that, understandably, that is why then, a lot of the drive in European regulations is to reduce CO2. That's, quite justified. So those are the regulated ones, but let's move swiftly on to the unregulated ones. So same vehicles. And first of all, if we look at the nitrous oxide, and N2O is interesting because it's a powerful greenhouse gas. So we gathered our samples onto tubes, in this case into molecular sieves, and then we have used a specific N2O standard gas bottle, so akin to the calibration gas bottles for PEMS, to quantify the amount of N2O seen, convert it to mass, divided by kilometers, and segment it into the urban, rural, and motorway. So we can see in exactly the same way as we see for the other pollutants how the vehicles perform. So what you can see is the highest emitting part of the driving clearly is the rural segment, and that's true for most of the vehicles. The lowest emitting is the urban segment. Obviously, because this is a greenhouse gas, the location of the emissions is not so important. And then I've highlighted in green and red, which are the lowest and highest, respectively, of the vehicles within each of the driving modes. So the Clio comes out as the lowest emitting in urban, but the highest in rural. And they're the sort of best and worst are spread reasonably evenly across the piece. So there's no one vehicle which stands out as dramatically cleaner or dirtier than any of the others. And a little bit later on, I will convert this to a CO2 equivalent so we can see this in the context of CO2 emissions, primary CO2 emissions. Moving on to formaldehyde. I mean, formaldehyde has many unattractive effects, from cancer to serious irritants of eyes, skin, and the like. Here this is the results from the DMPH cartridge, which we've then quantified using a specific formaldehyde standard. And again, you can see the highest emissions here in the rural driving. And the good and bad is not quite so evenly spread across the piece. So in this case, the Renault Clio is the highest emitting in both urban and motorway driving, and pretty high up on rural driving as well. Whereas the Kia Rio, the mild hybrid, is the lowest for rural and motorway and pretty low on urban. So for formaldehyde here, we are seeing more of a pattern, more of a formaldehyde as a differentiator in emissions performance between the different vehicles. Then if we move on to the polycyclic aromatic hydrocarbons and the nitrogen containing compounds as well, and these are of particular interest because of their carcinogenic nature, or many of them. Now here, I should flag up that for the purposes of this presentation, what I've done, we've quantified them all on the basis of a toluene equivalent. Now, what this means is that the milligrams per kilometer are likely to be overestimated compared to if each compound had been quantified with its own standard. So the relative measurements, absolutely stand, and that's what I wanted to mainly show today. And it's summing all the compounds in these two generic groups together. So what we see here is, we're talking of total emissions of the order of 200 plus milligrams per kilometer over the combined cycle on average over those vehicles. But then one vehicle stands out as undoubtedly the cleanest, which is the Renault Clio. Interesting in the context of the previous slide on formaldehyde, where this vehicle was the highest emitting. So we may be, beginning to see certain trade-offs, as we've seen on so many other pollutants before. And the Clio is almost an order of magnitude cleaner than the dirtiest vehicles here. Again, as with the other ones, the rural driving is the dirtiest part of the driving. Moving on, so that's the PAHs, and then the final group that I wanted to show, and this is not the all the different elements. I'm not putting up about the alcohols or the glycols. We are able to see all the VOC compounds from about C2 to C44, if not higher, through this technique. I've just focused down on some of the more salient groups for the purposes of this. So taking a group of alkanes, alkenes, alkynes, and cycloalkanes, which have a range of issues that they cause, from affecting lungs, liver, kidney, brain, giving you headaches, dizziness, a whole unpalatable bunch of symptoms, again quantified using toluene equivalents. So bear in mind the tendency to overestimate, but the comparisons are valid. Again, what we can see here, actually, that this one, rather like formaldehyde, is that there does seem to be more of a characteristic pattern by vehicle, i.e. some are cleaner than others. So the standout one here, which has the lowest emissions, is the Mini Countryman plug-in hybrid, and I emphasize this is done in engine mode. Whereas the Subaru Forester full hybrid was by some way the dirtiest or highest emitting, particularly in rural and motorway driving, of all the 8 vehicles. So this clearly seems to be potentially a differentiator across these vehicles. So bringing that, and before I bring that all together into a summary, there's to show our ability to actually go down to the individual species level. I wanted to show, firstly here, actually there's quite a lot of common compounds between all 8 vehicles. Compounds which are clearly identifiable and are there in material amounts. And this, I've just picked out the top 10. Actually, no, top 9 compounds here that are most prevalent and common across the piece. Now, you can see a lot of those are in the alkane group, with a few aromatics there as well, and the toxicity is shown there. And what this shows is there's a significant commonality around lung damage. Some of them have other toxicity issues in terms of skin and eye irritants as well, but the standout one is the degree of toxicity to the lungs. Now, obviously, this does depend, and the actual medical effects do depend on the concentrations and the amount inhaled or ingested by the human being, and of that I'm not going into today, but their presence in material amounts, and then when scaled across the fleet of gasoline vehicles, is why at least this is cause for concern. So that's the common compounds. The other way to look at it is, what are the differentiating compounds? So looking at those vehicles, I've tried to pull out which compounds are, if not exclusive, disproportionately prevalent to each individual vehicle. So if we take the Renault Clio, for example, what we can see by our speciated analysis is that 2-pentene is particularly prevalent for this vehicle and not prevalent for the other vehicles. And that compound is associated with irritation of lungs, skin, eyes. Not the same level of damage and toxicity as some of the other, but certainly an irritant. And then we can see through the others. So almost all of them have their own characteristic standout compounds. So the Volkswagen Polo has a benzene related compound there, which affects eyes and skin. The Kia Rio there has a particularly potentially carcinogenic compound, which is I'm not going to bother reading out, but you can see it on the slide. And again, these all are not just the differentiating ones, but they're in quite material amounts as well. Pentadecane is common between both the Octavia and the Forester, and also the benzene compound is in the 208, the Peugeot 208, same as the Polo. So this is quite an interesting way of seeing it when we're coming to benchmarking vehicles and understanding, what's similar and what's different. This is a good way of being able to drill right down to the individual compound level and see what is going on. So drawing that just together into a summary of these results then. What I've done is taken the urban-rural motorway splits and averaged them together, evenly weighted into a combined calculation for the whole EQUA cycle. That gives us the N2O figures in milligrams per kilometer, where the Octavia overall is the highest emitting and the Forester the lowest emitting. Then if we convert that to CO2 equivalents in grams per kilometer, what we can see is actually, on average, we're talking about only about 0.5 gram per kilometer increase. So that isn't significant in the context of 140 odd grams per kilometer average primary CO2 emissions. The N2O component on these vehicles does not appear to be adding materially to that CO2, the overall greenhouse gas effect. In terms of formaldehyde, the average is just over 0.2 milligrams per kilometer, with a sort of variation about threefold between the cleanest and the dirtiest. So quite a bit of variation there. In terms of the PAHs, similarly, about an order of magnitude variation between the best and the worst, around an average of 231 milligrams on the toluene equivalents. And alkanes, much higher quantities of over 4 grams per kilometer on that toluene equivalence basis. So by this method, we can see essentially what is possible. And this, in a way, is the tip of the iceberg as to what we can see at the tailpipe, and how we can see it segregated urban rural motorway, but also aggregated, but then taking it right also down to the disaggregated compound level as well. So there's the ability to see in a lot of detail, a lot of resolution in real world driving what is going on with these late model year vehicles. So just to wrap up then, so I mean, what are we doing with all this data? Well, it's being added progressively to the EQUA database. So this is our database that we've been compiling since the beginning, which is effectively standardized according to our EQUA cycle, independent in that we source the vehicles ourselves, and real world in that it's all on the road. And those are really the 3 watchwords for us. And that database can be used for benchmarking. As you've seen, we can compare between different vehicles, R&D to be able to work out, how to meet Euro 7 limits or whatever internal targets, and understand the trade-offs between different compounds, and to also have a concept of no harm as well, that there may be a low quantity, low concentration compound, but if it's highly carcinogenic, that is something that you need to be aware of. It can also be used for market surveillance, policy development, the like. It's deliberately designed to be complementary to the core work around the certification activity. We use the same techniques to do bespoke testing work. So where a client wants to do something that is not to go in the EQUA database, very confidential, we can use exactly the same principles, but that would then be bespoke and confidential work. And all in all, really, what we're trying to drive towards is the holistic environmental impact of vehicles, not just obsess about the tailpipe, work out, what are all the impacts. And I use the word environmental carefully as well, in that it's not just air as well. Increasingly, these things, the effect on soil and marine is becoming more and more important. So the 3 elements of the EQUA database, there's the historical regulated tailpipe emissions, which that's where we have 2,000 vehicles. Adding to it now these unregulated pollutants for the coming vehicles. But there are also 2 other areas as well. So we've been active in developing standardization for vehicle interior air quality. Now this is, we started by focusing on the ingress of particles into the cabin through the ventilation filtration system. And that's what we're standardizing through SEN Workshop 103 at the moment, which is quite well advanced and driving towards a conclusion in terms of publishing a method. But we are also conscious about CO2 buildup in the cabin from human respiration, particularly on recirculation mode. And now, using the same techniques I've shown here today, being able to look at the off-gassing of VOCs from interior materials. And that is a very important and differentiating factor between vehicles, and the concentrations, particularly on hot days like today, that VOCs can get up to in the cabin is potentially significant. And the third area is tire wear emissions. So and our focus has been on not a generic blob of non-exhaust emissions, but looking at tire wear emissions specifically, measuring them in terms of total loss of particles, but also the chemical composition of those particles as well, and what proportion of those become airborne and what go into the soil and water. And so that's alongside the interior air quality and the unregulated tailpipe. They are the new bits of the EQUA database which are being developed to complement the traditional tailpipe regulated data. So in summary, what I would say is that from the 8 gasoline vehicles that we've chosen across 8 different manufacturers, random sample, including different levels of hybridization, they're easily compliant on the current regulations today, easily compliant in normal real world driving. very comfortably so, except for CO2, which is, although not a non-compliance thing, it is, you can see, even whatever is being shown on NEDC, WLTP, the reality of it is that CO2 emissions are about 50% higher than where they should be. And that, given that that is our pressing environmental concern, that's why topics such as nitrous oxide emissions are so important. But we see that that does not add significantly to the CO2 equivalents. Formaldehyde, we're picking up formaldehyde. It's relatively consistent between driving modes, and we're seeing similar levels between vehicles, but it also is a differentiator as well. There are some that are cleaner than others. On the VOC side, and I have used the term VOCs, I really should use VOCs and semi-volatiles as well. This going up to C44 and beyond enables us to see these heavier semi-volatiles. What we can see is that there are hundreds and hundreds, if not thousands, I say 500 plus to be on the safe side. A lot of VOCs and SVOCs can be identified in the exhaust in real world driving, and some of them are highly toxic. And looking at those differentiators, we can say that each vehicle has its own chemical signature. Now, these VOCs, they affect health directly, and they also affect air quality through the formation of secondary organic aerosols. Where we need to go next is to understand the degree to which these affect air pollution and human health. Are they there in aggregate when added up across all vehicles on the road? To what degree do they actually have a material effect? So on that note, thank you